Hello. Hello everyone. Today we're talking about capacitors, but actually mostly we're going to talk about the electric potential and a little bit on capacitors. I know you study capacitors in school and charging and discharging, particularly capacitors. We will be looking at capacitors from a slightly different angle. So we're uh, well, using the Gauss law. And I just realized that I should place problem 2 first and then problem 1. So let's start with problem 2. And this deals with the definition of a potential, electric potential. So what does it even mean? Potential is the work done per unit charge to move uh, a, a small positive test charge from infinity to a point in the field. Point to point P in the field. Potential at point P. So what does that mean? Well, let's say we have an electric field. Well, could be, I don't know, could be a battery. Could be a battery. Let's say it's a 1.5 cell. And we know that the potential difference in a cell is 1.5 volts. Let's say we earth the we connect the negative terminal to the earth. The earth is always at 0 volts, so we can say that the potential in here is 0 volts, and the potential here is 1.5 volts. That means to move a charge from infinity, for every coulomb of charge, you will need 1.5 joules. 1.5 joules for every 1 coulomb of charge moved. And the important thing is the direction, is the way you move, it doesn't matter. This is an example of a conservative force, which means the route you take from infinity to that position doesn't matter. It could be a spiral, it could be anything. The work will always be the same. So the work done. So why would you need to do work? Well, because the terminal is positive. It's a positive charge, and you're moving a positive charge towards a positive charge. So you have to push it. You have to push it. Okay. A charge q is moved from infinity to a distance r from a fixed charge. So there's a fixed charge q, and point P, or some point, is a distance. Okay, let's make it simpler. Let's make it distance is a distance r away. And the work done to move from infinity along this line to this point. Okay. Now, let's say the small positive test charge is Q0. Q0 is a small positive test charge. Now, if it moves a small distance r, so this distance is dr, then the force that you need, so the force that you apply, obviously because the Q is a positive charge and this is a positive charge, so you need to push it towards that charge. The force, as we already know, is K Q0 Q over R. Or well, yeah, let's keep it as K. And the work done, is dW, the small amount of work, is force times distance, force times dr. Now, there is a catch here, which catches me out all the time. Now, dr is this small distance, but also dr is the change in distance, and change is the change in r. But r is decreasing because you're moving closer to the charge. So dr is negative, and that's why you have to put a negative sign here. Hope that makes sense. Because we know the work is positive. Obviously, the work is positive because you're pushing. Force is positive. Well, you can just take the modulus of the force. And then we know the dr is negative, so we have to take a minus. Minus compensates the fact that dr is negative. Okay. And let's substitute that in. So dW is minus F, so K Q0 Q over R dr. And we need to integrate that. So when we start moving from infinity, we've done zero work. And when we've moved to that point, we do W amount of work. That's the total amount of work needed that needs to be done. Then we integrate this from infinity to R. Well, where R is the final position in the field. Lovely. Force is R squared. Yes. Okay, so if we integrate this, so this is going to be W between limits 0 and W, minus K Q0 Q. These are constants, so those don't matter. R minus 2 dr from infinity to R. So minus K Q0 Q. And we integrate this. This is going to be R to the power minus 1 over minus 1 from infinity to R. So minus K Q0 Q. Minus 1 over R between limits infinity and R. So minus K Q0 Q. Minus 1 over R plus 1 over infinity. 1 over infinity is obviously 0. And we do plus K Q0 Q over R. And that's it. That's the work done. Now potential V is work done per unit charge, per small unit charge. Therefore, it's KQ over R, or Q over 4 pi epsilon R. So this is the potential at a point R away from a point charge. Q. Or in other words, aka potential of a radial field. Potential in a radial field. Okay. Now we're going to use that formula to solve problem 1. Okay. 2-point charges are placed 10 centimeters apart. So we have 2 charges plus 4 microcoulombs and minus 2 microcoulombs, and they're placed 10 centimeters apart. Find the electric potential at the midpoint. So we need the electric potential here. Now, we have the principle of superposition. Principle of superposition. Principle. Sorry, I forgot how to spell stuff. Why is the current flowing in the circuit isn't complete? Where is the current flowing? I'm not sure. Where? What are you referring to? With the battery, there's no current flowing. I'm not sure what the question is about. Right. So principle. Principle of superposition. Yes. Superposition. There's a moment of madness. Okay. Principle of superposition says that the total electric field is the sum of individual electric fields. That's E3 plus etc. How the positive particle can get a work done? Well, we push it. We take the particle and we move it. Yeah, that's, you can imagine in somebody's hand taking the charge and moving it from infinity to that point. Principle of superposition, the electric field. Now, this equation is not entirely correct because the electric field is a vector, and we have to put vectors in here. But the potential, electric potential, is not a vector, is a scalar quantity, and the total, sorry, not electric, the total electric field, and V total is V1 plus V2 plus V3 plus etc. So these are vectors, and these are scalars. And there's an important distinction. So, example, if you have a positive charge, let's say plus Q small, and a plus Q small, now the total electric field, because there will be an electric field that way, a vector, an electric field that way. Let's call it this E1 and E2. At the midpoint, the total electric field is E1 plus E2. And because they are in opposite directions, it's 0. But if you do V total, it's V1 plus V2, and both of them are positive. So that's, well, 2V1. Well, it's greater than 0. Not 0. It's not 0. That's what I'm trying to say. Because you're adding potentials at this point, at midpoint. So the electric fields will be 0. They won't cancel each other out. But the potential would not. The potential add up just like numbers. The potential is a number, like 15 volts, 17 volts. Hopefully that makes sense. Right, so we have a 4 microcoulomb. So the potential from the first charge is equal to Q over 4 pi epsilon naught R1. So the distance R1. So that's um well, let's use the other formula. It's slightly easier. KQ over R1. So that's K is 8.99 times 10 to the 9 times 4 times 10 to the negative 6 divided by R, which is 0.055 centimeters. Okay, so 8. 719. So plus 719,200 volts. That's the potential at P from the first charge. V2 is KQ2 over R, R2. So 8.99 times 10 to the 9 times 2, or negative 2, divided by 0.05. And that is, well, 2 times less, divided by 2. Negative 359,600 volts. And V total, V at B, the potential at point P is minus 719, 200. Oh, yes. 59,600 volts. Okay. Number 3. 3 identical charges are placed at the corners of a square of side length L. Find the total electric potential at the fourth corner. So we have four corners, and we need the electric potential at point P. That's the fourth corner. So Q, 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 side length A. So that's A, A, A. And let's call it the potential at P. Potential at P is equal to V1 plus V2 plus V3. Let's call it, this is 1, 2, and 3. This is vertex 1, vertex 2, and vertex 3. So V1 and V3 are the same because they're the same distance. So that's Q over 4 pi epsilon naught A. And V2 is less because the distance is bigger. It's square root of 2A. So it's Q divided by 4 pi epsilon naught square root of 2A. And yeah, so this could be written as 2Q over 8 pi epsilon naught A. And this could be written as square root of 2Q 8 pi epsilon naught A. So I multiplied the top and bottom by 2 here. I multiplied the top and bottom by square root of 2 here. And now we're just adding. So that's going to be V1 plus V2 plus V3. So it's 2Q plus root 2Q plus 2Q divided by 8 pi epsilon A. So that is 4 plus root 2Q 8 pi epsilon naught A. We don't need to simplify. We don't need to, we have simplified. We don't need to substitute any numbers because the answer should be in terms of A and Q. Okay, moving on. Nice one. A uniformly charged ring of radius r carries a total charge q. Find the electric potential at a point along the axis of the ring, a distance z from the center. So we have a ring, and the ring, you can think of the ring as made of tiny charges. Let's call it Q1, Q2, Q3, Q4, etc. Now, this is the axis of the ring, and you are at point Z, where this is the Z axis, and this is point Z, and this is 0. Okay. For the first point, Q, well, the total charge is Q. So if we assume the ring consists of n charges, assume ring consists of n charges. Each charge is Q over n. Q over n. I hope that makes sense. So the potential V1 from the first charge, is Q1 divided by 4 pi epsilon naught. And then the distance. Well, what is the distance? Well, if this is the radius of the ring, r, and this distance is z, and this is a right angle triangle, so we can say that this distance is square root of r squared plus z squared. Square root of r squared plus z squared. Now V2, in a similar fashion, is the same thing. So V2 is Q2 divided by 4 pi epsilon naught square root of r squared plus z. The distance is the same. Right, for charge 1 and charge 2, the distance is the same. So now we just need to add them, but we realize that this is Q over n over 4 pi epsilon naught r squared plus z squared, and q over n by 4 pi epsilon naught square root of r squared plus z squared. Therefore, the total potential is, well, the total potential at point z, Vz, is V1 plus V2 plus V3 plus etc. plus Vn, because there are n charges. And then we just Q over n plus Q over n plus etc. plus Q over n divided by 4 pi epsilon naught r squared plus z squared. And if you add these up, you just get Q, because this n times. So it's Q over 4 pi epsilon naught square root of r squared plus z squared. Okay. Six. So this is the electric field along the axis of a ring, of a uniformly charged ring. If you go further away, obviously this distance increases. An infinite plane sheet has uniform surface charge density sigma. Find the electric field. Well, we've already done this question. We've already done this question last session. Um, well, let's see. We used Gauss's law. We used Gauss's law, and we saw that if this is uniformly charged sheet, then it produces an electric field in an outwards direction. So it's an electric field like this. And we saw that this electric field is sigma divided by epsilon naught. 2 epsilon naught. Y2. Do I remember Y2? Well, oh yeah, because two different directions. Okay. Yes, we proved that in the previous session. So we used Gauss's law. Um, I'm happy to show that again. Flux is Q in over epsilon naught. That was the rule. That's the flux from an electric field. And then we had a charged plate, and we take an imaginary. Well, we can take an imaginary. We can take an imaginary cuboid, right? So this area is A. So the charge, so Q in, would be sigma times A, surface charge density times A. And then the total flux, which is A multiplied by E, so that flux penetrates this section. Now the field would be parallel to this side, so the flux through the top faces would be 0. The side from the front and back faces would also be 0. So we're only interested in the flux going from through the left side, so through this frame and through this frame. And therefore, that total flux is A times E, which is, well, actually 2A times E. And that's going to be equal to Q in divided by epsilon naught. And Q in is sigma A. So we have 2AE equals over epsilon naught, sigma A over epsilon naught. So A cancels, and we have the electric field, which is sigma over 2 epsilon naught. Hope that makes sense. This is Gauss's law. Lovely. And now determine the electric potential. The electric potential of the function as the function of distance from the sheet. Well, we know, so if this is the sheet sideways, and this is a point P. The electric field is sigma over 2 epsilon naught. Now we know that the potential is the integral of E with respect to dr, where r is this axis, or if you want to say distance, edr. So V is going to be the integral of sigma 2 epsilon naught dr, and which is going to be just sigma 2 epsilon r plus a constant. Oh, sorry, minus plus a constant. Okay, so well, that's kind of the definition of potential as well. And all right, so we have potential here. Now, what is C? Well, the problem is that at infinity, we normally say normally at infinity, V is 0. But look, at infinity here, no matter what C is, at infinity, V is not 0. No matter what C is, V at infinity, V of infinity is, well, not 0. That's kind of a problem, because you substitute infinity, you get minus infinity. Yet infinity is not 0. It's actually minus infinity. How does that work, you would ask? Well, because the potential at infinity is not 0. Why is it not 0? Well, because it's an infinitely big plate. And infinitely big plates do not exist. If it did exist, then the potential at infinity would be infinite. But it's not. And that's it. That's the explanation. Infinite plates do not exist. So this model just breaks down. So the don't exist. So no paradox. No paradox. Okay, so it's just we use this mathematical model, which works well for small distances, but not for large distances. Okay, I hope that makes sense. Number 7, we have a parallel plate capacitor has a plate area A and separation D. So we have a capacitor with 2 plates of area A, and they're separated by distance D. Now the electric field from the first plate, so let's say the plate, this plate is positively charged, and this plate is negatively charged. We know that a positive plate has an electric field which is equal to let's call it E1, which is sigma divided by or 2 epsilon naught. But the negative plate also has an electric field, which is incoming, which goes into the plate, which is E2, which is in the same direction, and it's also sigma divided by 2 epsilon naught. But sigma is area divided by, sigma is Q divided by area, and therefore charge is sigma times area. Oh no, so we can substitute that in here. So E1, the field from the first plate, the field of the first plate is Q over 2A E0, epsilon 0. And the field from the second plate is Q over 2 epsilon 2A epsilon 0. Now, obviously this is negative charge and this is positive charge, but the fields are in the same direction. So we can just take Q, modulus Q here. And we see that the vectors, two vectors in the same direction. So the electric field is 2 modulus Q over 2A epsilon naught. So 2 cancels out. And we get the electric field, which is Q divided by A epsilon naught. Now we need to find the potential difference between the plates. We know that the potential difference is the integral, minus integral of E dr. And we can say that it goes from 0 to D, from 0 to D, and actually no, let's do from 0 to D, the other way around. 0 to D, 0 to D, so the axis is this way, R axis is this way. And that's going to be minus integral of Q over A epsilon naught dr from 0 to D. And that's equal to minus Q over A epsilon 0 of R from 0 to D, which is minus Q over A epsilon naught R. So the potential difference is that. And now the capacitance is Q over V, modulus Q over modulus V. And so the charge over V, which is minus Q over A epsilon naught R, D, of course D, which is equal to, cancels, A epsilon naught over D. Oh, that's the capacitance of a parallel plate capacitor. And if the distance is the plate separation, how does the capacitance if the separation is doubled? So if D is doubled, we see the capacitance will increase. Oh, sorry, decrease. C will halve. C will halve. And capacitors, capacitors labs. Okay. And you can see this is the capacitance of a capacitor. And if I move the plates closer, the capacitance increases. If I move the plates further apart, the capacitance drops. So moving them closer together. Right. Now, if I want to further increase the capacitance of the plates, I can increase the area. So increasing the area and moving them closer together makes the capacitance bigger. And this is the reason why capacitors in uh, series and capacitors in parallel. If you take capacitors in parallel, so imagine you have C1 and another capacitor C2. It's as if you're having, if you move them closer together, if you move C2 closer to C1, you kind of get C1 and C2. which is which is equivalent to having just one capacitor, one bigger capacitor. So if you if you think about it, like two capacitors in parallel is the same as, well, having one bigger capacitor, well, one capacitor with bigger plates, and that's exactly what it is. So it's C1 plus C2. So for capacitors in parallel, the total capacitance is just the sum of the capacitances plus C2 plus C3 plus etc. All right. Now, if you're thinking of capacitors in series, then in series, now a very good way of looking at it is if you have a capacitor C1, another capacitor C2, then if you were to move them closer together, capacitor C1 and capacitor C2, you can eventually make them into just a bigger capacitor. So it's a capacitor with a bigger plate separation. So C, bigger distance, right? So you have C1 and C2, and overall, it's just having a wider capacitor. So if you imagine you squish them together, you get one capacitor with a bigger plate separation. And you can see that C total is less than C1 plus C2. Well, actually, it's less than C1 and less than C2. And the total capacitance total is less. And therefore, so 1 over C total for series capacitors is 1 over C1 plus 1 over C2 plus etc. Just like resistors, but the other way around. Resistors. I hope that makes sense. Okay, so where's the question? Two capacitors are connected in series across a battery, right? Find the equivalent capacitance. Well, they can connected in series. Well, we've done that. We saw that. So C1 and C2. And this is a battery of EMF epsilon. Find the equivalent capacitance. Okay, I will attempt to do this in a slightly different way. So imagine that, so this is a positive plate, this is a negative plate. So if you have a positive charge here, Q1, there will be a negative charge on the opposite plate, negative Q1. And then if you look at the second capacitor, it will have a positive charge here, Q2, and then a negative Q2 charge here. But if you look at this part of the circuit, you can see that this part of circuit is isolated and the total charge has to be conserved. So initially when the battery was disconnected, the total charge in this section was 0. Because as charge is conserved, minus Q1 plus Q2 must be 0. Once again, before the capacitors were connected, the total charge on the two plates was 0. So we definitely know that the charge on each capacitor is the same. Hence, Q1 is equal to Q2. Now we know that if we replace this with an equivalent capacitor, which is just equal to Q, the capacitance. So we also know that V1 plus V2 is EMF. And V1, what we know about capacitors, V1 is if capacitance is Q over V, so V is Q over C. Yeah, so V is Q over C. So it's Q over C1, Q1 over C1 plus Q2 over C2 and equal to Q total divided by C total. But Q total, if you imagine that these two capacitors are replaced with a single capacitor, or with a capacitance C total, it would have the same charge. So it would have the charge plus Q's here and minus Q here, which is the same as Q1 and the same as Q2. Which are this so Q total. Q total is the same as Q1 and the same as Q2. No, it's not the sum. The total charge is not the sum because the total charge is just placed on the outer sides of the outer edges of the capacitor system. And therefore, we have these cancel out. And we have 1 over C1 plus 1 over C2 is equal to 1 over C total. And that's it. That's another way of proving. Well, it's the way of proving using Kirchhoff's laws. So this is Kirchhoff's second law. Show how the voltage is distributed across the capacitors. Well, we know that V1 plus V2 is the total battery. So Q over C1 plus Q over C2 equals EMF. And therefore, well, we can write V1 is Q over C1 and V2 is Q over C2. And therefore, V1 to V2, the ratio of V1 to V2 is reverse, is C2 over C1, is inversely proportional to the capacitances. All right. So find the equivalent capacitance, 1 over C1 plus 1 over C2. Or you could write C1 plus C2. No, so 1 over C total. So therefore, C total is C1 C2 over C1 plus C2. And the ratio, so V1 to V2 is the same as C2 to C1. What happens if C1 is much greater than C2? Well, if C1 is much greater than C2, then all the voltage would be so all the voltage would be the biggest. You would have a bigger voltage on the smaller capacitor. The smaller capacitor will have a bigger voltage. So smaller capacitor will have have a bigger voltage. Okay, and finally, I want to talk about charging a capacitor. So imagine you have a capacitor and a resistor and a switch and a battery. So charging. So this is problem 9. Charging a capacitor. So this is a battery, so that's EMF. The capacitor has capacitance C, and this is a resistor R. This is also known as a CR circuit. CR circuit. Good. We will also be studying later on LC circuits. LC circuits. We will be studying LR circuits. Well, not really LR circuits. Well, yeah, LR circuits. And we will be studying LCR circuits. Okay. So basically, we're interested in how the capacitor charges. So how does the voltage on the capacitor changes as time goes by? So we close the switch, and we want to know how the voltage changes as time goes on. To do this, we're going to write Kirchhoff's second law. Second law, which simply says that the voltage on the battery is the voltage on the resistor plus the voltage on the capacitor. We know that the voltage on the resistor is IR, and the voltage on the capacitor is Q over C. But we also know that current is the rate of change of charge, delta Q over delta T, which when you make it a limit to when T tends to 0, it's dQ as over dt, which tends to dQ over dt. So we can write EMF is dQ over dt R plus Q over C. Okay. Yes. And this is a differential equation. So EMF, C, and R are constants, and Q and T are variables. So we're going to separate the variables. Separate variables. And we're going to, so what can we do here? We want to do EMF minus Q over C equals R dQ over dt. We're going to multiply everything by dt and divide everything by E minus Q over C. You know what? We're going to multiply everything by C dt. So C EMF minus Q dt equals CR dQ. Now we divide both sides by C EMF minus Q, and we get dt equals CR dQ over minus Q plus C EMF. I don't like this, so I'm just going to change the signs and put the minus somewhere else. I'm going to put it here. It doesn't really matter where I put it. Okay. And now I can integrate. I can integrate this from 0 to t. So time starts at 0. And Q, well, it's from 0. Initially, there's 0 charge. And this is Q final. Q final. So this is minus t. Minus t equals CR. And this is the logarithm. Logarithm modulus Q minus C EMF. And it changes from 0 to Q. And we can now write this is minus T over CR equals logarithm Q minus C EMF modulus minus logarithm Q is 0 logarithm C EMF minus C EMF. Minus obviously goes away. And here, well, Q is changing from 0 and the maximum value of Q is 0. So this is a negative value. Okay, so they force us again to, so it's a logarithm of C EMF minus Q, right? Because so Q minus C EMF is less than 0. So actually, when I took out the 0, I shouldn't have done that. I've messed the whole thing up. Doesn't matter. C over C EMF. Okay, and now I can rewrite this as C EMF minus Q over C EMF is equal to e to the power minus t over CR. And this is going to be 1 minus Q over C EMF is equal to E minus T over CR. 1 minus E minus T CR times C EMF, and that's equal to Q of T. That's how the charge changes on the capacitor. And you can sketch that. You can sketch that as Q and T. And this is going to be like this. C EMF. Because that's Q final. C over EMF. And yeah. And now we know that the voltage is Q over C. So we just divide both sides by C. So V of T is equal to well, EMF over 1 minus E minus T over CR. So the voltage on the capacitor changes in the same way. And just the final value is EMF. And if you take for the resistor, so current is V over R, then you can say that current, no, you can't do that. Sorry, I've got a small distraction here. So there are two ways you can approach the current. You can say current is the voltage on the resistor, divided by R. But voltage on the resistor is EMF minus voltage on the capacitor over R. Sorry. Yes, you can help. EMF minus VC, and EMF we know, EMF V of C. This is V of C. So EMF minus EMF plus. Sorry, sorry. Times EMF minus T over CR over R. So EMF cancels, and we get EMF over R. That's the initial current. That's the initial current through the. Oh, jeez, just a second. EMF over R is the initial current, so it's I0 E minus T over CR. I'm almost done. So yes, the current as a function of time is I0 E minus T over CR. I could have done it in a different way. I could have differentiated this expression. If I differentiate that, current is the derivative of charge. Yeah, so, and you would have gotten the same result, I0 E minus T over CR. And you can sketch the how the current changes as in time, and it's an exponent. It's an exponent, but it's a decaying exponent, I0. And finally, I can show it. Well, I'll try to show this to you. So fit AC circuits, and if you take a battery and a capacitor and a resistor, and take a switch and measure the voltage on the capacitor, and look what happens. So 3, 2, 1, close the switch, and you can see that the voltage does behave the way that I have described. So open this. Oh, we need to let's do a discharging circuit as well. Discharging capacitors is just as fun as charging them. And close the switch, and the voltage goes down like this. Okay, switch open, switch closed, charge slowly, slow and steady, and then discharge. So, bottom line is capacitors are incredibly fun. Um, I'll leave you to that, and I'll see you in 2 weeks' time, and we'll be talking about some maths. So, see you in 2 weeks.